All right, so in this video lesson, we are going to learn about line integrals. Okay, before we really get into line integrals, allow me to give, this can be a brief lesson in case you haven't learned that formally prior to this particular video lesson here, or this can be a brief review, okay, of the idea. But now, before we get into really learning about line integrals, we need to discuss about the orientation of a space curve. All right. And so this is the idea right here. So space curve for anyone up to this point is very familiar, okay, and is nothing unusual at all. So let's say I'm just going to bring up a very simple, quick example right here. Let's say in a 3D space, right, with the three axes right here, then we have, let's say we have a point in space being 1, 1, 1, and we have another point being about 5, 1, 4. And so let's consider the path. So through any 2 points, we can draw a path. So here, let's consider the path here as being a straight line. Okay, let's consider a path that being a straight line going through the 2 points here. So it's clearly a space curve, even though here, it's specifically for this example, it's a straight line like that. But in the end, generally, it's a space curve. It's a curve. It's a trace that's going on in space like that. Okay, and so with this space curve right here, a path is just a path, okay? But now think about, you have learned, now this is something that we definitely, anyone learning this video should be already familiar with. But let's consider a parameterization here. So I'm going to consider the parameterization where, so this curve here, we call it C, right? Now this path here is C, but the first parameterization I'm about to give is, okay, so x equals 1 plus 4t, y equals 1, and z equals 1 plus 3t. Okay, so, and again, for anyone learning in this lesson, according to your previous learning, then you should be able to come up with the equation of this line, right, going through the 2 points right here. So with the 2 points, 1, 1, 1 and 5, 1, 4 right here, going through the 2 points and come up with parametric equations. So this is one of them. And so the set of parametric equations here is indeed referred to as a parameterization. So this one right here is, so now in a more formal name, is parameterization. All right, parameterization, something like that. And so, and then we advance a little further into calculus, and we learn that when we specifically learn about vector value function, a parameterization, a parametric equation, a system of parametric equations here is equivalent to a vector function R of t. So this same parameterization C1 right here, it can be understood as a vector value function where R of t, I mean x of t, see, x is a function of t, so we have 1 plus 4t, and we have 1 for y, and we have z equals 1 plus 3t. Okay, so the same system of parametric equations, now we see that as a vector value function. Okay, and now think about this same parameterization. So parameterization can be given either as a system of parametric equations or a vector value function. And so in this way right here, think about t is the interval, okay, the parameter t is the interval from 0 to 1 for this particular parameterization right here. Okay, and so now think about it this way. When t, okay, when t equals 0, because it's always the way that we start. So we start the value because on the interval specified earlier, it's t is going from 0 to 1. So when we start at t equals 0 for our parameter, then clearly according to the system, then we're looking, we have, okay, so for this start right here, then we have the point, we are right at 1, 1, 1 for x, y, and z, because x, y, and z is calculated by this system of equations. Okay, and so then we start, and now at the end of our interval for t, so when we're ending out t right here, t reached to the end when t equals 1, because the interval for t is only from 0 to 1. So as t changes from 0 to 1, think about on the line right there, we have a particle that starts at 1. When at that t value to be 0, we have a particle on that line being at 1 physically on that path at that location. And then when we're ending there, then of course at any other t value between 0 and 1, then we have a point on that line between the 2 points. But now the point changes to 5, 0, 1. Comma 4. Okay. And so when we're starting with t equals 0, we're at that point. When we're ending with t equals 1, we're at the point 5, 1, 4. So that means in this picture, as t is changing from 0 to 1, then we think about if we place a particle, as I've been saying, then the particle is moving this way from 1, 1, 1 to 5, 1, 4. All right. And so now in that way, how you're seeing it, you think about we use a parameterization to describe a motion, to describe the motion of a particle that we place on that. And then the motion here has a direction where it goes, and that's what orientation means right there. Okay, so this parameterization here gives an orientation, a direction of where a particle is moving, where the particle that we put on the line is moving. So here with this parameterization, we describe the situation that the particle is moving from this point to that other point. Okay, and so in just that same way, now in your learning, a path is just a path. A line passing through the 2 points here is just a line. So once again, just rolling back to the very beginning problem, we got that physical line right there going through the 2 points. Okay, but what if when we were, I got to remind anyone, but when we were learning how to find the parametric equations of a line in space, then there was not only one parameterization. There are other ways of writing your system of parametric equations. So aside from what we've seen earlier, we can come up with the system of parametric equations as following. 5 minus 4t, y equals 1, and z equals 4 minus 3t. Okay? Or in vector form, and you can call this parameterization C2. It's the same curve, but it's parameterization number 2 here. And then you can see C2 as the vector value function being 5 minus 4t, okay, 1 for y, and 4 minus 3t for z. Okay, so in your experience coming up with parametric equations for a line, what we have seen earlier for C1 was not the only system of parametric equations, and there are many other ones out there. There are many more. There are many other ones out there. So I'm pointing out 2 different ones for a good purpose here. So, and again, for this one right here, let's just say for this parameterization, right? It's clearly now a parameterization. So we're going to just consider this parameterization for t variable, t parameter changing from 0 to 1. So the values for t is again from between 0 and 1. But now think about this. When we start our t parameter as a start, we start at t equals 0, just like the way how it is in the interval. And then, but that means when we're substituting this t into the that parameterization that we're currently at, then we're looking at physically on the path, we will stay at the point 5, 1, 4. We're starting there first. And then when we're ending with our t parameter value, when we end at t equals 1 right there, then the point, if we think about it, we place a point on that path right there. It started at this, equivalent to t equals 0, but when we're ending with t equals 1, the point, the particle moves to 1, 1, 1. All right, and so with this quick chart right here, going back to the picture, you can see that with this parameterization, it describes a different orientation, And so a path is a path, but an orientation, that's why here in my title of discussion, there are more than one, there's multiple orientations, even though on the same curve. Okay, so for this particular problem, this parameterization here describes the motion that if we place a particle, the particle is going to start here when t equals 0. And it moves in this direction, and heading to 1, 1, 1 when t equals 1. It's a completely different a completely different orientation already. All right, and so at the end right here, so in the end, here's how we're formulating some of our understanding right here. We can see that a space curve, or just generally a curve, right? Any curve in R2 or R3. So a curve, including line, okay? A curve in R2 or R3. I specifically gave that demonstration in R3, but it should be the same in R2. Think about R2 is when you have that x and y floor, right? You got a path right here. You got a path, and then an orientation means a direction. Either you are going from one point, from this point to there, or you're going from this point to here. That's an orientation. It makes a difference. So each orientation here has its own parameterization, that as you have seen in my demonstration earlier. But now let's write down the formal wording of that. So a curve in R2 or R3 is oriented. Okay. All right. So just like that, like how I pointed it out earlier, the line, okay, in space right here, just a segment connecting the 2 points, just a segment. But now we're going this way, that's one orientation. That means we have just now oriented. We specify a direction. If a particle moves along, if a particle travels along this path right here, we have specified a direction where it's going from where to where. That's what it means by the curve is oriented. All right. And then further from what we have investigated previously, then a parameterization. Okay? A parameterization. Okay. A set of parametric equations that described our motion right there. Okay. A parameterization gives an orientation. Okay. So one parameterization is equivalent to an orientation. Okay. An orientation of a given curve. All right. And that's the idea right there. Okay, so that's what it means by orientation of a space curve. We need this understanding before we move on and take that into the line integrals and doing line integrals, because the big idea of line integrals is based on the orientation of a parameterized space curve. Okay. All right, and so now at this point we are ready to learn about what a line integral of a scalar function is. Okay, so let's dive into that. So for as a journey waiting ahead for you, well, line integrals is what we're doing in the line integrals is the biggest picture. Okay, but then there are two major types here. There's a line integral for scalar function, and that's what we're heading into right now. And then after that, once we're fluent with this, we're going to drive that idea into line integral, but for or of a vector, okay, of a vector field. And that's the idea. Or for short, we call that just line integral of a vector, okay, or a vector line integral, whatever that is. Okay. So there are two major types of line integrals problem right there. This is where we're at right now. All right. And so to have a good idea, allow me to really throughout a good major amount of time for this particular topic right here, line integral of a scalar function. I'm going to have to keep dividing that into two separate works right here. Two separate the zones right here. One for 2 variable functions and one for 3 variables functions. Because scalar function can go. Now our study here is going to focus on scalar function of 2 variables or scalar function of 3 variables. So in the case of 2 variables, okay. When we're looking at the case of 2 variables, then think about we're given a function. We're given function f of x comma y right there. Okay, and then so scalar function is known to be above an x and y floor or the x and y plane. So the line integral now is the idea is about we're trying to take an integral over. We take the scalar integral over this line. At this point in your learning, a line is not necessarily just a hard straight line, but it's more like a curve. A curve on the x and y plane is also considered as a line, right? A boundary line like that. Okay, some kind of bent line, or more specifically, is this curve like that. So we got a curve, an oriented curve. So this curve here is called C on the x and y plane. you don't even need to see this curve as a function f of x or whatever, because the function is f of x comma y. It's a surface on top of that. And then we're trying to find the integral along this line. All right, the integral along that line. So then we got so many lines here, x and y floor. We can have a line that's going like this. We can have a line that's going like this. Okay, but oriented. See, these lines are all oriented on the x and y plane. There are so many lines, so many curves out there. All right. So now you got to keep in mind a couple things, right? See, C, right, is on the x and y plane. Yes, and C is oriented, meaning we have some kind of there will be some kind of parameterization describing this. So to be precise, C can be described as a vector value function or of t being some two components, right? X of t, comma y of t. That's a parameterization right here. For t is in between some value from a to b. Okay, so that's the case of a two-variable function. So very similar right here. Very similarly, we are looking at for the case of three variables. So when we're looking at function of three variables, right? Our function here is given to be some function f of x comma y comma z. Okay, then a line is now understood really as a space curve. So in the 3D space, okay, we have, see, x-axis, y-axis, and z-axis. We can have a curve going straight or bent or whatever. But this curve C right here got to be an oriented curve right here. Okay, so it got to have some oriented. So I'm drawing that way, just one orientation. It could be traversing this way. It could be traveling along this way right there. Okay, and so just like that, similarly, okay, C is in R3 space. All right, and then C here, yes, is oriented. All right, and then C can be described as a set of vector value function, or as a vector value function x of t, okay, y of t, and z of t. Okay, and then of course we allowing t to change from, t is changing from some interval a, in an interval from a to b. T is changing from an interval from a to b. All right, so that's the two different versions right there. And so now the idea is like this. So now for line integral, let's now talk about, doesn't matter whether the curve is, you know, on the x and y plane or the curve is in space right here, but just think about a one portion of the curve. We got start, we got an end right here. Okay, let's say that the curve is being oriented in that way right there. So t equals a is here, that's the beginning, and t is equals b at that point, the ending of our curve. So physically on this curve right here, we're going to break that down into many sub-partitions. Okay, we partitioned the curve right here. All right, and so, and the more we do, the better it is. That's the idea of integral. An integral is accumulation. So the first thing is that we're breaking up the entire path right here into so many sub-intervals. So let's say the change between this point to another point, right? The change between this point or another point right here. We're going to call that, this is being a vector value function, right? See, there's the origins right here. Then to that point, it's a vector value function, or I right here, and or I minus 1, and then to that point right here it's an or I. So the change right here is the difference between or I minus 1 and or I. Okay. But now with this here, what is important to understand is that, see, after we breaking that down into so many sub-intervals, right? So many sub-segments right here, then this is some r sub I minus 1 point, and this is some r sub I point like that. And so the space between, so of course it got, no matter how small it is, but it's still got to be somehow a certain bent level right there. It's being bent at a certain level. But the more we're breaking it down, right, the more sub-intervals we're breaking it down, then each of these small sub-segments right here is close enough. So I'm going to take an extracted out version. So an extracted out version, okay, so r sub I minus 1 is here and r sub I. What we have here is this arc right here is close enough to the actual straight distance between r sub I minus 1 and r sub I. So this distance right here, okay, we're now going to call that, it's a delta S sub I. It's a piece of arc right here, we call it. Okay, but approximately close enough to that straight segments where we call it delta S sub I. Okay, delta S sub I. And so there are so many delta S sub I right here. Let me use a different color ink right there. So these are all straight, even though they look close enough to being, I mean, these are all bent, but even though they look close enough to being straight already. So think about, there's a straight line between these 2 points. There's a straight segment between here. There's a straight segment here and another straight segment there. And that's the idea right there. Okay, so each one of the red one here is a delta S sub I. All right, and so let's understand about delta S sub I a little more. Delta S sub I, see, I pointed out a picture that from the origin, wherever that is, pointing to this point is r I sub 1. And it's a vector r, right? Again, r sub I right here. So because this curve is parameterized. Okay, has a parametric equation, set of equations. So delta S sub I right here is indeed just simply the length from Ri minus 1 to Ri. That means the length in our understanding of vector is the norm of R sub I minus R sub I minus 1. Okay, or it's the magnitude, okay, in proper vector language right there. It's the magnitude of this difference between Ri and Ri minus 1. All right, and so that's what describes it. So the idea now, and let me clear out the picture here and make the picture tighter so that I have more space to write down here. And so in that way that we're looking at the picture, and we got so many of them. So the idea now is that in each of the arcs right here, in each of the arc, which is close enough to a delta Si right here, I am going to pick a point. So here I'm going to pick a point that I call that. So this is equivalent to some delta Si. So at the ith subportion, okay, at the ith subportion, I'm going to pick a point that I call that some R star I, some R star I. So why is it R star I? I mean, this is Ri sub 1. This is Ri. It's all any point in space in our understanding up to this point is a position vector. So at some positions that I choose in here as a sample point, some position vector I choose in this arc, I call it R sub I. I mean R star I right here. Not necessarily on this point or not necessarily on that point, even though it could. Okay, so again, the x and y axis system is here, right? Ri sub 1 is here. Ri is here, but R star sub I is here. Okay, it's the sample point, right? It's some sample point on that arc at the ith interval. All right, and so, but then each R star I right here is the same as X star I, Y star I, Z star I, if it's in 3D. If it's in 3D, or it's the same as just a pair of X star I or Y star I, if it's only in 2D. Either one of the form like that, it's going to work. And that's why it's more convenient to write that commonly as Ri right here, so that it includes both cases, either in 3D or in 2D like that. That's what it is. Okay, and so the idea of a line integral with the scalar function is that with our scalar function, doesn't matter if our scalar function is f of x comma y in 2 variables, or f of x comma y comma z being a function of 3 variables, being a scalar function at any point x comma y or x comma y comma z. We can understand this as this is f of r. Because now on that path itself right here, then each point is a function, is a position, so you can call it R of t. See, f of r of t, okay, where r is the vector position, and the same here. It's all boiling down to that same form. So we can save ourselves that headache about writing down the two versions, 3D or 2D, right there. Okay, and so in this case now, this is how I'm seeing it. Back to this arc right here, 2D space or 3D space. Pick a point like this, right? We call that R star I point like that. Then we're gonna multiply the scalar value function. So the function's value at that point, R star I. We're gonna multiply that with this length right here, delta S sub I. We multiply that, we get some kind of quantity. We get some kind of quantity. All right? We get some kind of quantity. And then we're accumulating all of them. So we're accumulating by summing up. So now you have to understand, if you break this arc of yours into 1, 2, 3, 4 sub-intervals, then you're going to have to sum it all from I going from 1 to 4. But if you're breaking it down into like n, right? If you're breaking it down specifically or generally for n sub-intervals, and you sum it all of those, so on each little segment right here, on each little portion right here, then you have to go f of r sub I times or multiply with delta Si right there. And then we sum in all of those from beginning to the end. But then doing this work right here, we desire the precision. We desire to get more accuracy and better accuracy. So we keep breaking it down into more sub-intervals. More sub-intervals. Okay? And so in that way right here, more sub-intervals means we're going to keep increasing n to infinity. All right. So ladies and gentlemen, doing this work right here, our work becomes the following. This is how we come. See, as we're taking n to infinity, right, this delta S sub I here becomes the differential ds. Because when it becomes so small to the point that there's not much difference anymore between Ri and Ri minus 1 anymore, and that delta S here becomes just the differential ds. It's a small, infinitesimally small change in S. So that's the ds. And then R star sub I right here, when the interval becomes so small, it becomes just simply the function value at R. And R here is the some points, right? That's not even distinguishable anymore between the Ri minus 1 and Ri, because it comes so close to each other. So f sub R. Okay, I mean f of r, but r here, think of that as in a 2D case it's a x comma y, or in a 3D case it's a x comma y comma z. Okay, and then the accumulation here, we're summing up all of those. So now in a concept of this problem right here, then we're accumulating all along what? It's an integral. We're accumulating everything all along the curve C right here. This curve C, all along the curve C. So ladies and gentlemen, this is what we have. So we call that the line integral of a scalar function. Our function here is a scalar function, and we're taking the integration over this bent curve. Okay, either in a 3D space or in a 2D space like that. Okay. All right, so now we are ready for a final definition. All right, so for 2 variables and for 3 variables. So an integral like this is called, okay, of a function. So with a given function, f of x comma y, being a function of 2 variables. And so with the function value multiplied with the infinitesimally small differential ds right there, along the curve C that you have described, that you have seen right there. This integral, this line integral of a scalar function is defined to be the function at R star sub I, okay, multiplied with delta S sub I, okay, and we take the summation for I going from 1 to n, and we increase the number of subintervals to infinity, okay, and that's one way how you're seeing that. And then in the case of your function being a 3 variables function, f of x comma y comma z, multiplied with ds, okay, accumulating or taking the integral of that along a given curve C, a curve that's parametrized, okay, then that's the same as if we take the limits, or we take the Riemann sum, and this is, by the way, it's Riemann sum. Yeah. function f of r star, okay, sub I multiplied with delta s sub I here. When we take the limits as n go to infinity, I going from 1 to n, okay, and then in a case of a two variables right here, then the r star, okay, each r star I right here is the same as a pair of value x star I and y star I. Okay, if you would like to use that in place of the Ri, that's fine. And in the case of a three variables, it means the same as, see, R star I point is the same as the triplets x star I, y star I, and z star I. All right, so that's how we define a line integral, right, of a scalar function, and this is the version for a two variable functions, and this is a version for a scalar function being of three variables. Okay, and so, but there are a lot more. Right now we just began right there, and I have just only given out the definition of what it means by being a line integral of a scalar function. All right, and so now let's look even a little further right here. So I'm going to have to really draw the space curve over here, and again, it's an oriented curve, right? It has a starting point at t equals a, equivalence for the parameterization, and t equals b here, and then along the path here, the curve C here, we're breaking it down into so many sub-partitions. And going with equal sub-partitions is ideally the idea, but I failed to draw that equal sub-partitions. But anyway, so each one of these, the red ink is the delta S. In the big version, okay, the red ink is the delta S. So think about each of the delta S right now, which is close. I mean, which is a lot of time close to the actual arc like that, okay. And then again, the reason when it gets so small, right, when we break into more subintervals, and delta S gets closer and closer to the actual arc like that in that subintervals. But now let's freeze a certain instant where we have a finite number of subpartitions. Then the delta S here, let's look at that even further. For delta S, right, on the x and y plane right here, on the x and y plane specifically, okay, delta S, we understood that delta S here on the x and y plane, right, this is just any straight segment right here, that's delta S. So as a triangular setup right here, there's a delta y here and delta x here, okay, that's according to my picture, delta y and delta x. All right, and so that means the Pythagorean theorem says that delta S squared equals delta x all squared plus delta y squared. It's a right triangle right there. Okay, and now advancing further on this, yes, that means delta S itself is a square root of delta x squared plus delta y squared. Like, no one can argue about that. Okay, and so that means when it gets to the infinitesimally small version, where remember we keep breaking it down the same arc, but we keep breaking it down into infinitely many subintervals, then to the point that delta S become ds. Then so that means this when it becomes ds right here. So ds equals square root of dx squared plus dy squared. This formula becomes that when we're breaking it down into infinitely many delta S. Okay, and so in that way, now remember the fact that the C here is parameterized. C here in case of a of a two-dimensional on x and y plane, and C here is parameterized by R being the x of t comma y of t. And so in that case right here, the dx, see, in that case, let me open a side note right here. See, x is a function of t, so dx as a differential dx is relating to x of t right here. It's x prime of t times dt. Okay, dx is x prime of t times dt, and then the same here, the dy differential, okay, is y prime of t times dt. We've learned this idea previously back, in the days that we were learning about, in the lecture that we were learning about parameterized curve and space, when we specifically learn about space curve and we're taking derivatives of space curves and all that. So that means I'm going to take these expressions and substitute that in there. And so my formula here becomes a square root, right, of x prime of t dt all square plus y prime of t dt all square. And so that now means in one further step, ds here equals to, and now each one of these has a common factor of dt square and dt square. So anyone viewing the video lesson here should be comfortable enough with the algebra, so I can start picking up the pace. But I'm gonna factor out the dt square and pull it outside of the parent of the square root. So here I'm looking at x prime square plus y prime of t square, and then multiply with dt. Okay, because the truth behind the scene is, see right here, it's x prime of t times dt plus and all square, okay, and then plus y prime of t times dt. So as a common factor here, we got a dt square being a common factor. So I pull it out as a common factor and even take it outside of the square root. So going through the square root, it eliminated the square on the dt. And so ds here, we have found a successful expression for ds. ds equals to x prime of t square plus y prime of t square, all inside the square root times dt times the dt. Okay, so that's the 2D versions, how it goes from delta s square, and I made my argument that ds is expressed as this. Okay, and then let me put aside this understanding right here. So that's on the x and y plane. So that's the how we express ds on the x and y plane. So what about for 3D? Okay? What about for 3D? Think about in 3D space right here, right? Think about in 3D space from a delta s right here, right? And we make the same way. Delta s is indeed turns out to be, it turns out that delta s equals the square root of the delta x square plus the delta y square, but additionally plus the delta z all square inside the square root right here. That's what's happening in the 3D space. And so in that way right here, with the very similar arguments, we're going to come to the following. Delta s in 3D is the same as the square root. What I have now is x prime of t, okay, square, plus y prime of t square, and plus the third component, z prime of t square, okay, dt. Because again, recall that for a space curve, a curve in 3D space, right, the vector value function is expressed as a vector of three components: x of t, y of t, and z of t. All right. And so now in this way right here, at this point we have successfully formulated the expression for ds in the equivalent kind of space in the xy plane R2 space, or on the 3D space x, y, z, and then x and y and z space like that. And so, but both versions here, we all come down to one general conclusion. See, this is x prime of t, and then this is y prime of t, and then square here. In the end, if we look a little closer and link back to what we've learned in the old days, any one of these is the same as. Okay? So in the end, we've made the following conclusion. That's very important. And either one of these come to the same one. ds is, any one of these is the expression that's indicating r prime of t, the derivative of the vector value function. Doesn't matter 2D or 3D. The magnitude of that vector value of the derivative of r, like that, multiplied with dt. So that's the square root expression brings into that. And so we have come down to the general expression for ds, the magnitude of the r prime vector, like that, okay, multiplied with dt. All right. And so that's an alternative way of seeing it. Okay. Alternatively, we see ds as this right here. That's really generalized the two cases, being in the 2D plane or in a 3D space like that. Okay. And so at this point right here, generally speaking, point in 2D in 2D space or a point in 3D space, okay, can all be equal to generally a vector value function R of t, okay, and then and of course the vector value function of t right here is being is a position on that curve right there, either a 2D curve or a 3D curve, C like that. Okay. So the vector value function has to be a position on that curve. And then the work I've done on the other board to generalize that doesn't matter if you're on the xy plane or on the 3D space. We can all alternatively write it. Or we can all arrive at this important expression, this fundamental expression for ds right here. And then generally, as that includes both cases, then generally ds is expressed as the magnitude of your r prime vector multiplied with dt. So from that way, we actually have formed a theorem. So there are nicely worded version of this theorem in any textbook that you are using, but allow me to write the brief versions here. But see, commonly or generally speaking, a line integral for a scalar function, so for a scalar function f of r right here, see, either 2D space or 3D space or 2D space, we all call that a position point on the curve. So that's why it's f of r, okay, or more precisely f of r of t, okay. And so with f of r of t right here, if f of r of t right here, the line integral that we've intended to do, the line integral accumulating all of those function value at the points multiplied with ds that you have seen earlier, the accumulation of all that along the vector curve, along the curve C right here, is proven to be just simply, yes, it's f of r of t again, but multiply with C instead of ds, it is that expression r prime of t in magnitude dt. And then after successfully turning this into that expression, we're just simply accumulating, take the integral from a to b, because this curve C right here is a parameterization taking account that t is changing anywhere from a to b. Okay, and so we have formulated a way to calculate a line integral for any scalar function that runs along a curve like that we are integrating along a curve. Okay. So now at this point here, we are ready for our first example. Let's now call that example 1 here. All right, and so let's get into the problem right there. So this problem is asking us to evaluate the line integral, the accumulation of this scalar function. It's a function of 3 variables, a scalar function along this curve C right here. So that's why the scalar, a line integral always comes with the ds according to to what we have seen in the definition. And now we are accumulating this expression along the curve here, where the curve C in space has a given parameterization, cosine of t, comma, sine of t, comma, t right here. So it's a vector value function given here. And furthermore, t is given only changing anywhere from 0 to 2 pi. Okay, and so to start setting up with this function, right, that's the starting setup right here. But to get started into evaluating this actual line integral on a scalar function, see what we have here is a scalar function. Then we do the following. Recall for yourself that ds is, according to the theorem, ds is r prime of t in magnitude, the magnitude of r prime of t times dt. And so let's work it out with that expression right here. Get for yourself into that habit right there. So r prime of t here is going to be, so it's the magnitude of that vector. So r prime of t is minus sine of t times, comma, cosine of t, comma 1. So the vector inside here is the r prime of t. So we're taking the magnitude of that and multiply with dt. And that's the expression that represents ds right here. And so now we're looking at the square root of minus sine of t all square plus cosine of t all square plus 1 square dt. Right? And then with our understanding at this point in trigonometry function, that gives me a sine squared plus cosine square, sine square of t plus cosine square of t. That gives me a 1 right here with these two terms and plus another 1. So we have a square root of 2 dt. And so ds is indeed equals to square root of 2 dt. All right. And so now the theorem, as a reminder, the theorem said this integral f of x, y, z ds equals the function at the vector value. That means, and then multiply with delta the magnitude of r prime of t dt. We have already found this to be square root of 2 dt. But see, r of t right here is substituted inside of f. That means that we're going to let x equals to whatever. We're going to let x equals the cosine of t, because that's the parameterization for that. And we're going to let y equals sine of t, and we're going to let z equals t. That's the parameterization for this current curve. And so we're going to substitute these right here into our function. And so according to that theorem, according to the theorem that we have done right here, then the problem becomes the following. Okay, the line integral for x squared plus y squared plus z squared all multiplied with ds, we're looking at setting it up as the integral. Now x now becomes a cosine squared of t because it's x squared, and then y is substituted by sine. Okay, so I'm looking at plus sine square of t plus t square. That's how I substituted x, y, and z by the corresponding cosine of t, sine of t, and t, like that. And then the r prime of t, the magnitude of r prime of t with dt, that was simply the square root of 2 dt that we calculated earlier. And so now the parameterization here, as a reminder, the parameterization given here is in respect to t changing from 0 to 2 pi. So the t parameter for this parameterization changes from 0 to 2 pi. So in that way, the integral, according to the theorem, is an accumulation from 0 to 2 pi on this function. All right. And so now cosine square of t plus sine square of t simply comes out being just a 1. So we now, our integral reduced to something that within our reach completely, an integral from 0 to pi, okay, for 1 plus t squared times the square root of 2 times dt. All right, and now we can just bring out that common coefficient there, and then from 0 to 2 pi, okay, 1 plus t squared dt. And now we're just going to carry out this integral in the usual way right here. So that gives me square root of 2 times t plus 1/3 t cubed, and evaluating this from 0 to 2 pi. All right, from 0 to 2 pi. And so that's all together square root of 2 times 2 pi plus 8 pi cubed over 3. All right, and then we can do some further simplification of that expression, but I don't feel that any necessary the practical need for that. So I'll just leave it that in this thing in this expression right here. But that's how we have done as easy as it can be, right? A line integral for a scalar function. That's how we can do, and that's how we will do any of the line integral for scalar functions along a given curve with a given parameterization. Okay, and so the major theorem is here. So for from a to b and t changing from a to b. All right. All right, and so now we learn about, we're gonna make our way into how to calculate line integral of a vector field right there. Okay, so now let me illustrate the idea with the theoretical idea and the concept of that. So now 2D or 3Ds, it's all going to be just, the one breaking down as following. So now we imagine that we have a space, right, in 2D curve or 3D curve. And you have seen that in my earlier demonstration when we were learning about line integrals over a scalar function. But for line integral of a scalar function over a curve right here, then a curve in 2D or in 3D, it has a parameterization. Okay, so when t equals a is here, that's the start, and that's the end, t equals b. We're breaking it down again into many subintervals. Okay, and so each subinterval right here, yes, this is, let's say this is some ith subinterval. So we're looking at Ri minus 1 and Ri right here. And so here we're going to pick a sample point right here, and we call it as the R star I. So all of that idea is very, very familiar from what we've done earlier with the line integral on scalar function. And so now the idea of line integral of vector field now is that at each of these sample points on a given path right here, okay, and of course this path is going maybe one orientation from t equals a to t equals b. So yes, and here we have to understand the c is given, okay, c is given by some vector value function. Could be 2D or could be a 3D. And so now at any sample point arbitrarily chosen in a delta S space right here, okay, right here again we got a delta S sub I. Okay, it's supposedly a straight segment, but nearly equal to that actual band arc right there. And so the idea now is that this line exists in a vector field. So the vector field can be a 2D vector field. Okay, it could be a 2D vector field where there are a whole bunch of vectors, right? A vector pointing this way, a vector pointing that way, a vector pointing that way. We've learned about vector fields before we got to this lesson right here. So if anyone is not familiar with what a vector field is, this lesson is definitely not for you yet. Okay, so now if at any point here we got the idea of a vector field doesn't matter if 3D or 2D. A vector field now, so any point, even and including that point we choose on the path, has a vector right there, that being positioned right at that point. Okay, and that's why I draw a vector right there. So the idea now is that, see, at any other point you got other vectors, here you got another vector right there. So the 3D case is the same. You can draw, okay, x-axis here, z-axis here, x-axis, z-axis, and y-axis. Okay, and then there's a space curve, and so there's your vector field D right there, the vector F. All right, and so the idea now at each point right here, the vector F is called a vector F at the point R star I. So I no longer have to worry about the 3D or 2D, because just using a general idea, a point in space is an R point right there, and a point specifically in an either subintervals, and we choose that as a sample point. We call it the R star I right there, okay, at any general either interval. And so, and let me now even take away the axes here, because it's making my picture a little too busy. The idea now is that doesn't matter 2D or 3D. Think about calculating work. The whole purpose of vector field is that think about the force field. That's for anyone who has done some physics, right? The force field or the fluid field right there with the in 3D space or whatever 2D space, or the wind blowing, right? As the flow of the wind right there, there's a whole vector field that describes the wind blowing right there. And so at any point, right, the force exerted by the wind, or the force exerted by the water flow, or the force exerted by the whatever magnetic field or whatever is a force. But then right along on that line, right, think about along the line. So right here, if you move the particle on that line, along that line, so along the line we use a tangent vector. I call that the unit tangent vector. Okay, so T here, capital T here is your unit tangent vector, and you should have learned about what that unit tangent vector back in your days learning about vector calculus. I mean about learning about vector function, vector value function. So briefly, the unit tangent vector is r prime of t, okay, divided by the magnitude of r prime of t. That's a reminder right there. But the main thing about the unit tangent vector is that it's a tangent vector and it's length 1. It's length 1. And so now why do I mention about that? Because the thing now, the idea is, think about now, again, I keep mentioning about force. So force, but being exerted in a distance that's indicated by a directional vector. And so force, right, at that point we got a force, but exerted in a direction indicated by the vector t, right there. And then more specifically, the vector t is always length 1, but the vector t multiplied with the delta s sub I, multiply with the little magnitude being the length of delta s sub I. Then at that point we have a vector tangent, but then long enough to be about the same length as that. Okay, and so that's distance multiplied with force there. So in general, as a vector concept, is a dot product between the force vector and the displacement vector. Okay, this is now precisely, this is the displacement vector, and then this is force at that particular sample point right there. So force dotted with the displacement vector. What we're having here will become a little small amount of work, and we call it it's a work done in that ith subinterval. So this part right here is a work. Okay, that's one application of that. But in the end, generally, what I want you to see is right here. See the vector at that point, dotted with the displacement vector, right? That's why it's unit tangent vector multiplied with the length delta si right there. And then with that dot right here, right? Now we're going to accumulate all of those, a little work from all of these. So each of these sub intervals, we got a little work amount. So we're accumulating all of them. We're summing it up. And so on this board, I'm doing the following. Right? The force by determined by our vector field right there at any sample point in an either subintervals, dot products with the unit tangent vector, in scalar products with delta si. Okay, this right here, we take the sum. Okay, we're summing up all of those from the first partitions to the nth partition, and then the idea now is, again, if doing that, because again, when we're breaking it down to a finite number, then there's always a difference, some difference between the actual arc and the real delta s. So that's why we want to break it down as many as possible, so that the length of the arc come closer to the actual ds, delta s right there. Okay, and so in that way, in that concept, again, we're taking the limit as n goes to infinity. Okay, so let me refine my notation a little bit. It's a summation. Okay, I running from 1 to n, and we take limits. We would like to continue increasing the number of subintervals to infinity. Okay, all right, and so very similar to how I have explained in our understanding previously about the line integral on the about line integral on the for scalar function. Then when n is arbitrarily large, right? It's becoming continuously large right here. Then this ds, this delta s right here become a ds because it's so small. The interval becomes so small to the point that the arc. Okay, right now we got an interval big enough, but we keep breaking it down so that now the delta s is really close to ds, and we keep breaking it down further to the point that delta s becomes all of the ds uniformly in size like that. And then the vector t is always tangent at any point, so we got t times ds. But this vector is in dot products with the force vector at r. All right, and for short, we don't even have to write on the r anymore. It's just the force vector by the vector field right there, dot with t ds. And then the accumulation here becomes an integral along the curve, like that, an integral along the curve. All right, and so that's how the integral, the line integral for a vector field came out right there, being given as the line integral along the curve C right here for the vector field dot with t ds, and that is defined as a definition, defined as this Riemann sum, and we're taking n to the part to infinity. Okay, so that's this, and the t vector is still here. Okay, and so and now as far as a formal definition. So now in a given vector field, be a given vector field. Right. Then the integral where we have f dot t ds, accumulating that along the curve, right? The integral f dot t ds along the curve, the space curve C is defined to be, right, f at r star I multiplied, and then in dot product with t times delta si. Okay, and then we take the Riemann sum where I equals from 1 to n, and we take the limits as n goes to infinity. And this is how we are defining our line integral, right? So this one right here is the line integral. All right, of the vector field F, right, along the parametrized curve C right there. That's a definition. And then the better worded definition of this the better worded version of this definition is given in any of the standard calculus textbooks you can find out there. Okay, and so allow me to just hit to the main core point right here, and I'm using the minimized version of the worded version right there. But that's how we understand about what a line integral of a vector field along a curve is. Okay, and so now in just that same way right there that I've done, then this ds that we have seen right here, this ds right here is exactly the same meaning. The ds I'm seeing here is exactly the same meaning with the ds that I have made arguments earlier. This ds that comes from the delta s right here has the exact same meaning with the ds that I have explained when we were taking line integral of a scalar function. And so now in that way, my point is that similarly, or you can say same arguments, right, from line integral for scalar function. Right, with the same argument from there. Then we have the ds expression right from here. This ds expression can be expressed as the magnitude of the vector r prime of t multiplied with dt. Okay, and then of course for C is given by the parameterization r of t, some r of t, either a 2D or a 3D. Okay. And so now at this point, after you've seen the definition of the formal definition of what a line integral is, a line integral here is specifically along a vector field. Okay, and so now let me show you a few other various forms of how it's written, it's notated. So the notation right from our definition here is this. We got the force field, right, or a vector field F in dot product with the unit tangent vector and multiply with ds. Okay, and I tend to write that with parentheses, but usually it's not even requiring to have parentheses there. So this is one common form, okay, along the vector c. This is one form that you a lot of times see, but then there are quite a few other alternative forms of the exact same line integral on the vector field right here, but I gotta point it out right there. So it's all come out from the fact that, again, I wrote this down, I've written this down earlier, but now I'm going to repeat that one more time. For your curve C being parameterized as a t, as an R of t, then the unit vector is always R prime of t over the magnitude of R prime of t. This is a known fact right there. And we learned this from the previous calculus course, or the earlier portion of multivariable calculus. So from that right here, then think about, we're going to substitute this expression here for the unit tangent vector in our formula. And so right here, we're looking at the integral becomes the following. Okay, that integral, we got the the vector field f, or any vector f in dot product with, but now t is R of t, R prime of t, over the magnitude of R prime of t, okay, ds. It's just simply a substitution that I substituted this expression for t. And then further, according to what I've had on the board earlier, same arguments from the work that we were doing for line integral for scalar function. The ds is famously the magnitude of R prime of t times ds, times dt. And so in that case, I can use this information and substitute that for ds right here. So in the next step, I'm looking at the integral along the space curve C of the vector f being in dot product with R prime of t as a vector over magnitude as a scalar of R prime of t, okay, and times, so now, and it's really a multiplication, so times the magnitude of R prime of t times dt. Okay, and then of course in the way how dot products work, then you can purposely multiply this scalar with that other vector right here. And so that means what? These two expressions here can be cancelled away. And so in the next step, I'm seeing that expression here becomes an integral along a curve C right here, an oriented curve C right here of f dot R prime of t times dt. Okay, so we've gotten somewhere. So nail down this form. Put this form in a box right here. This form is exactly the same as that form, but this form allows us to do the calculation. Because here's the thing. You see, when you're actually doing the calculation, then think about it. It's going to be the integral, and of course, with your curve here is being parameterized by the vector r here, then f here is going to be the vector field, but vector determined at a position vector r. Okay, because the position vector r is a point in either 2D space or 3D space. And then with that, we take the dot product with r prime of t dt, and then now it becomes all in terms of a scalar vector, and we are integrating from a to b. This is the interval where t belong to, okay, from a to b, because this is the interval for your t parameter values that parameterize your curve C right there. So this is the way how we're doing it. Okay, this is the way how we're actually doing the work, and we can use that as a theorem right here, as a theorem. But now I am not going to stop right here. So make a good note of this. This is a formula to do the calculation. But then let's continue on further into this. I'm just still diving further into the written expression, of a problem right there, of a line integral for a vector field right there. So just in terms of a written notation, then now I can erase this away. And let's look further. Now R prime dt. Think about a vector r, a vector value function r of t. Then r prime dt is just simply r prime dt really is r prime dt really is the differential of dr. Okay, r prime dt is the differential of dr right there. Because think about it. Okay, if it's a large r, in a 3 space or whatever space right there. Some r here and some other r. Delta r is this change here, but as the interval keeps broken up smaller and smaller, it becomes a dr. And dr really is the r prime times dt. And so now we're seeing it the other way. R prime times dt is dr. So dr is a vector now, but a vector indicating an infinitesimally small differential change in r. And so now the differential of r right here, all I'm seeing that now is this is a more commonly seen right here. It's an integral along this curve C where we have f dot dr. All right. So ladies and gentlemen, this form right here is also a very commonly used form. Commonly used. Very commonly used right there. Okay. And so this form right here is just a way to get there. Okay, the way to get there but this one right here, aside from this one, aside from this notation from our definition, this is another very commonly used form right there, indicating it's a line integral of a vector field along a curve right here. All right, instead of this form. So these two are exactly the same, and be ready that throughout the assignments that I give or throughout the many problems that you see from textbooks right here, textbook authors mostly use this form right here. All right, and so now I'm short of space here. I'm going to move over to the other board. All right, and so now that we know for the same vector, for the same line integral, right, along a curve C for a vector f dot with dr here, we can continue writing this down even further. Now, again, in that same argument, dr is r prime of t dt. And again, remind yourself that because you see the c is given as r of t, okay, r of t. And so now I have to really tear it down into 2D and 3D versions right here. So for 2D versions, then r of t is indeed, yes, just simply x of t and y of t. And so consequently, dr being r prime of t dt will become simply the vector x prime of t dt, okay, comma y prime of t dt. And that means further in our work right here, okay, dr dot f here. And of course, f in a 2D case right here, f is a vector of 2 components, vector field of 2 component p comma q. And so f dot dr, okay, and integrating that along a curve right here is the same as okay, the integral where we got p comma q, okay, dots with all of this, okay. And again, and I should have also added in one more step. The x prime dt right here is the same as the dx, as the first vector in our dr, and then this is here is the same as a dy differential. So with this one right here, back to this one that I was saying, I ran really out of space. So it's the same as the integral of p comma q, right, dots with the vector dx comma dy. And so another very common form to see as well. That's we have an integral along C right here where you got p dx plus q dy. So ladies and gentlemen, this is another form that's very commonly used out there. Not as commonly as this, but it's also very commonly used, indicating the exact same line integral. It's just a different way of expressing it. It's expressing that in terms of the p and the q components of the vector field, like that, instead of writing down just generally the f. Okay, so P and Q right there, and then the dx differential and the dy differential. So these are not the two terms. These are not terms of this. This is just what I'm saying here. This is just an expression, a general expression, indicating we have f dot dr. Okay, but it's not two terms. It's not separately two terms really. So don't break this down into two separate integrals and do the work. It's going to be completely wrong that way. All right, and so same way right there for the 3D versions. All right, so for a 3D version, and just like that, right, then we got dr right here. Can be argued that it's the same as okay, x prime of t dt, y prime of t dt, and z prime of t, okay, dt. And so that can be further argued that it's dr here can be the same as the vector dx, because that is dx, okay, comma dy, comma dz. Okay, because all of this here is dx differential, of that here is a dy differential, similar to what we have seen earlier. This is dz differential. And so in that way, f dot dr, okay, the f dot dr is the same as, and of course f here is a p, q, and r here, okay, for a case of a 3D. And so that means we got p, q, r dot with dx, dy, and dz. All right. And so that means alternatively for the exact same line integral right here, the line integral along a curve C for the vector field f dot dr. Okay, that line integral can be expressed as a line integral along C where you got p dx, because the dots product here means p times dx, right, plus q times dy plus r times dz. So p dx plus q dy plus r dz right here. And again, ladies and gentlemen, this form right here is another form very commonly used among textbook authors and math professors out there to indicate a line integral exactly the same as this line integral, but it's just a different way of notating it. And again, I had that same misunderstanding when I was learning it, and it took me a little while to understand. But now this doesn't mean the three terms, okay? It's just one integral, but it's just a way to represent that as a dot product between the two vectors here, the vector f and the vector dr. All right, and so that's how it's done. So I gotta prepare you for this. I gotta prepare you carefully for these different variations of the symbols of the notation before we can successfully do any example problems. All right, so we are now ready for an example to calculate, so that we can learn formally how we can calculate the line integral on of a vector field right here. So continuing in the same video lecture here, let's call this now example 2 here. But example 2 is intended for calculating a line integral for a vector field. Okay? All right, so this is our example 2 right here, and it is the first example where we're learning how to calculate a line integral on a vector field right, along a curve C right here. So take your time writing this down. All right, so to get started with this problem right here. Now, as a picture of the path right here, we have a point, right? So the curve here is a point from 1, 1, 1. So, and we're connecting that to this point right here, okay, 5, 1, comma 4. So we have a line going through right there. And so you have to understand, the intention is already given in this problem. This curve here is oriented, it's an oriented curve. So it's going from 1, 1, 1 to 5, 1, 4. So that means the orientation is going from here to here. All right. So now in a different video lesson, you will learn about how we can give a parameterization. And the word of giving parameterization is very flexible right there. My parameterization is not the only one, okay? And you will even learn that later on. But then for now, the parameterization I can see for this, the most common parameterization for this, where it describes a particle moving on this path, moving from 111 to 514, that parameterization can be given as following. I can come up with how about R as a vector value function. Allow me to write it that way, being a 1 plus 4t, comma 1, comma 1 plus 3t. Okay. And then so this parameterization takes a point on this path right here. This parameterization makes the point move from this point to that other point. And so the direction is going this way in the picture. All right. And so, and for anyone who had some background, who already learned about how to come up with equation of a line, parametric equations of a line in space right here, going from 1 to 541, you should be able to agree with me with that. So you can apply your skill independently and come up with something that agrees with my parameterizations here. So my point here is, in this example, you need to be able to find a parameterization, but these are usually simple, that you can come up with one easily, and I don't need to get into how we find this particular one. So now, once we have found a parameterization that describes the orientation of the curve from here to here, right? And so this parameterization, of course, having t value going from 0 to 1 here. Okay. So that's the interval restriction for that. All right. And so now getting really into calculating it, doing this calculation right here, doing this calculation is the same as rewriting it, and I've pointed out that formula earlier. We're integrating along the curve C right here, where we have the vector field evaluated at R of t. And R of t is given, and I had it written on the other board right there. And then this vector right here is going to be in dot product with the R, the dr can be expressed as, okay, as R prime of t times dt right here. Okay, so this is one way how we can handle it. R prime of t times dt. So we have all access to our needed information right here. And so recall for yourself that x of t is 1 plus 4t. Okay, and then y of t is 1, and z of t equals 1 plus 3t. So this part of your integral here, that will become it's the integral, right? And f now is going to be the vector. So 1 plus 4t, that's times, because it's xy, so that's times 1, because xy, right? Comma, and then now I have yz, so 1 times the z component is right here. 1 times 1 plus 3t, okay? Comma, and then I have xz, okay? So, or zx, so I have 1 plus 3t substituted for z, and then the x value here is 1 plus 4t. So all of this here as a vector is the x component, y component, and z component is for the vector f at R, f of R. And then we would like to take the dot product with, okay, so from here, now allow me to imply that R prime of t is the same as taking the derivative. It gives me what? The derivative of x right here, it gives me simply 4. The derivative of y is a 0. The derivative of z is a 3. Okay, so we take the dot product with 4, 0, 3. Okay. And of course, multiply with dt. And so now in that way right here, we don't need to beat around the bush by using the c here anymore, but over the curve c here happening for t changing from 0, okay, to 1. Because on this curve right here, okay, t is changing from 0 to 1. That's how we parameterize that curve. Yeah. All right, so we have come to this form right here. So now all we have to do is just expand out this dot product. So I'm looking at, so now as the next step right here, it's the integral from 0 to 1. Right? And then in my work here, it comes down for me 4 plus 16t, okay, plus a 0. So that's dots with 4 right there. That's why it's 4 plus 16t. So these two components multiply together. And then 0, no, that component is multiplied with 0. Okay, it gives me 0 multiplied with that component, it gives me a 0. And then the third term right here is going to be 3 times, right? And I have 1 plus 3t times 1 plus 4t. Okay, and then all of that is now completely a scalar function in terms of t. We're integrating in respect to t right there. All right, and so that's how I'm working with that. And so in a few more steps, right, then our integral comes out. So at this point right here, all we do is just do the algebra on this and come out with a final integral form as following: an integral from 0 to 1. So, and I said earlier, it takes a few algebra steps. You go from here down to that next form I'm about to write. So what we have here is an integral from 0 to 1 of 7 plus 37t plus 36t squared dt. All right, and with this final integral completely in terms of t. And so again, as we go along with this example, let me remind you, this formula, this part right here is the real formula that allows you to do the calculation. And you can treat it as a theorem, but instead of writing that formula as a theorem to crank through your understanding, I'll just wrote it down on the board earlier, and here we'll keep using it. And this is just a common way of writing it, writing notation. Okay? And so with this integral over here, our final answer is going to come out being, and that's going to make it 29 plus 37 over 2. And altogether, 95 over 2. All right, that's our final answer. All right, so we've learned how to calculate a line integral for a vector field right there, and that's how it's done. So this form right here is a primary form that we need in order to really have access to the real problem and do that as a usual the integral problem. And now for your learning, I would like to introduce another example. So here it's example number 3. Okay, and this example is intended for you to try independently. Okay, it's intended for you to try independently right here. So the integral is as following. The problem is as following. We want to have the vector field being xy, yz, and zx. Okay, it's that vector field. So you can notice before I'm finishing up with this problem right here, the vector field is exactly the same as the one you've had in example 2. All right. All right. So now you can go ahead and spend some time copying down the problem and start proceeding. Okay. And so before you get started, I just want to mention, you can notice that this vector field right here is exactly the same as the one you have had in example 2. So I'm purposely bringing this up so that you already have some idea of how it's done before, and so the problem here is meant to be very similar. The only difference is that we have a different parameterization. So I'm saving you from calculating I'm saving you from coming up with your own parameterization. So you already have had a given parameterization. So the only difference between this example here and the earlier problem in example 2 is that we have the same vector field, but we're integrating over a different curve, over a curve that has a different parameterization. Okay, but now I want you to be aware, this parameterization, even though it looks completely different with the earlier one, it's actually when you draw the picture of that, if you put in a picture of that, it's still going to give you exactly the same path. It's exactly the same path. Okay, it's exactly the same path where we go from 1, 1, 1 to, and the same path, I mean the line right here, going from 1, 1, 1 okay, to 5, 1, 4. Okay, it's the exact same path connecting to these, but it's just given as a different parameterization. Because in what I said earlier is that for the same path, right, and the same orientation, we can also even come with more than one parameterizations. So what if for the exact same setting of the problem, the exact same path and exact orientation, we are looking at a different parameterization? So now, but then for your case right here, when you get into it, just take that as simple as you can right here, in a sense that you already had a given parameterization. Take your work, do the work. Okay, take your time, do the work, right, and come back with me. And I'm only going to show the final answer here, and then we're going to learn from the final answer instead of going through the formal work here on the board. All right, and so at this point, I hope you have had some time, you've spent some time solving, going through the work and learn to calculate this line integral on your own right here. The answer come out, the answer should be exactly, okay, the answer that should come out exactly 95 over 2 again. All right, that's the answer. And so now, what's the intention of an example like this? The vector is the same, the vector field is the same, right? The curve is the same, and the starting point, the ending point is exactly the same like that. The only difference is the parameterization. And so we still ended up with the exact same answer. So the only thing changed is the parameterization. And so now in that way, we draw out from one example, from one important understanding right here. All right, so again, I just want you to notice the answer here that you have tried and the answer we have done in example 2 together is exactly the same. And the only difference between the two problems here is that we got different parameterizations of the exact same path from the same starting point to the same ending point. And so the answer came out the same. So the important conclusion we want to make here as a remark, okay, as a remark, very important to keep in mind right there. That's anytime you're doing a line integral, right, over a space curve C right here, and the line integral f dot dr. Okay, this line integral is indeed the way we're calculating it is the answer that come out is independent. Okay. So doing the work it's independent with parameterization. Parameterization. All right. Upper C. All right. So what does that mean by doing this line integral, or the answer of this line integral is independent? The outcome of this line integral, the value of the line integral here is independent with the parameterization of the curve C right here. So now, this important observation here allows us to be more confident that, hey, just a path connecting from some starting point to another starting point. Okay? Once you have the path given, now with the same given physical path right here, the same given path, and with starting and ending point, you can come out with some parameterization. Your friend sitting next to you can come out with a different parameterization, but both of you come out with parameterization that agree with the exact same fitting of the curve right here. So my point again, in our learning about writing down parameterization for a curve, you see a curve and including starting and end point right here, just one curve like that with certain starting and ending point has multiple parameterizations. It's completely okay. And so now this observation here allows us to be more confident that doesn't matter which parameterization you going with, as long as your parameterization makes sense with the way how the curve is described. How the curve is described in terms of physically what it is, straight line or bent line, and in the right orientation. Okay, then whichever parameterization that is, your work will be the same value, will turn out the exact same value. And that's why in example 2, the exact same curve, right, that I had some parameterization given. And in the example 3, in the exact same curve, like that, exact same the orientation, but we got a different parameterization. Okay, but the answer, the outcome came out exactly the 95 over 2. Okay, exactly the same like that. Okay. All right, and so now at this point in your learning about line integrals, I have made this sketch earlier, and now I have to repeat it again. So line integral there are two major types here. There was line integrals for or of a scalar function. Okay. And then line integrals of a vector field. And so in one lesson we have learned it all. We have learned it all. But then admittedly, and at least in the way how I see about learning this, eventually line integrals of vector field will have a lot more application, and you will see this a lot more often. Okay, it's a lot more popular out there compared to line integral of scalar function. But why do we always have to spend? I teach this class, and in some other time I teach the exact same class, and I teach many generations of students. But anytime teaching line integrals, any instructor who is responsible would teach how to find line integrals of a scalar function. And even in my philosophy, I feel it's always best to learn how to find line integrals of scalar function before learning about line integrals of vector field right here. So why is that? What's my philosophy, how I'm seeing it? You see, and like I said again, even though admittedly eventually it seems like this one here is more fascinating, it will have more applications. The later theorems that you've learned throughout your learning time right here, in your remaining learning time with vector calculus, will focus on line integral for vector fields like that. But why did we have to spend some time to learn about line integral on scalar function before this, even though this thing doesn't have as many applications? The idea is that, see, when you look back closely at the line integral for a vector field right here, okay, and the primary form I introduced was here. But see, yeah, so now we call this as a line integral of a vector field or whatsoever, but in the end, if you isolate out this part right here, this f dot t part, in the end, that will finally become a scalar function. And the ds is essentially exactly the same in the way how I have explained that earlier. The ds here is exactly the same. And so with the ds here being exactly the same on a curve right here, your function here can be a 2-variable function or a scalar 2-variable function or a scalar 3-variable function. It's all bringing you back, even though you're working with a line integral for scalar vector field. You still in the end bringing yourself back to a line integral for a scalar function right there, because the f dot t quantity right here will eventually be a scalar function like that. Okay, and that's the idea right there of line integral. So it seems like two major types of problems right there. Yes, those are two major types of problems, but in the end, it's all breaking down to this one kind right here. So we learn this sort of like to train ourselves to be fluent with the skill, how to find line integrals in respect to a certain arc. Okay, in the xy plane or in space curve, and then be able to accumulate that over with some scalar function multiplied with that. Right, and that's the idea of a line integral like that.